What's up, guys? Have you ever wondered how ChatGPT works? Well, I've been using it pretty much everywhere I go, and it's been quite frustrating that it's such a black box that I put something in there and somehow you get a text output out of it. So I wanted to figure out today how it actually works and try training one for myself. And the data I trained my AI on was a PDF of the Almanac of Naval. And he's basically a super rich guy who's giving a guide on how to be rich and be happy. But here it is. So the way my thing works is really simple. It trains the AI on this data, tries to predict the next word. But for cost reasons, I'm gonna be predicting the next letter. This is gonna be the starting context that it'll keep predicting off of. So I'm gonna write how to get rich. And this is what the model outputted. So I wrote out here how to get rich, and it continued just of more easy wealth. Now, right now, it's not exactly accurate because I didn't train it for long. So you can sort of understand it, and you can sort of not understand it. But yeah. Although of course, with enough time and more compute power, it'd be able to train and generate much more better text. Now, how it actually works uses something called a transformer. But before transformers, we had something called RNNs and LSTMs. And an RNN looks like this. It takes the text data and then sort of processes them and outputs them sequentially, all in order. The reason we need this fancy architecture in the first place is because of memory issues. You see, in data like an image, you can pass the whole entire image and the AI will understand it. But when it comes to text, you have data like this and you have data before it, which means you must process the data along with the context before it. And that's what these models are created for. Now the issue with them is that they actually aren't really good at remembering things. And due to their sequential nature, like this, it limits them and just constrains them a lot. Meaning you can't just throw a bunch of GPUs at it. And the way it actually memorizes things is that while processing the data, it sort of stores its stuff in a hidden state, which you can think of like a memory box. But the issue is, say you have text over here, and you're trying to get to text over here. The further it is, the more harder it is to actually remember and store all in a box. And so LSTMs were invented to sort of mitigate that, and it sort of looks like this. It's more complex, has a bigger memory window to context from. However, the same issue arises when there's bigger text. And also the fact that it's still sequential. A transformer was invented to solve those issues. What it does originally was take one set of data and turn it into another set of data. Hence, transformer. But the GPT model, all it does is continue new text. So we don't have this part. We only have this part of the data. And the two key differences that separate a transformer between an RNN and an LSTM are something called self-attention and positional encoding. Now for self-attention, the way it works is simple. It simply ties each word's importance in relation to one another. So say you have the word I love the dogs. Now the word the would be more important to the word dogs than it would be from I to dogs. And so that's quite literally the gist of self-attention. And so theoretically, with enough compute power, a transformer model like this can have infinite memory. Now the thing about self-attention is that it's not reliant on sequential order. So you can just compute it all parallelly this time. Except, if there's no sequential order, you gotta tell the model what the positions are. The other key fundamental shift in transformers is positional encoding. it simply assigns a number, a position. And anyways, back to the original transformer model. So first of all, you have the output embeddings. Now the way that works is that, say you have some text, but the issue is, AI is simply a bunch of math. And you can't just plug a bunch of text in something that calculates with math, right? And so what happens is that these words get mapped out to an individual number. And then those numbers are mapped out into a vector space, which is also called an output embedding. Now the hope of this is that similar words like dog and Pomeranian would have similar numbers. And so once we have that there, we calculate the positional encodings and sort of add that to the output embeddings. Now we add it in hopes that the transformer, this giga beast, will be able to understand which positions are. And so once we have that done, that's when we actually put it through self-attention. Now the difference is that instead of a self-attention by itself, you combine them together with multiple self-attention heads. Because if you only had one of them, you would actually lose very valuable information while computing. And what we're gonna do with this encoded text is that it's gonna go through the AI network and then turn them into a value, a query, and a key. You can sort of think of it like a YouTube search bar. It's gonna map your queries against a set of titles, descriptions, and authors, and then show you the videos. Also, over here, it mentions masked multi-head attention. Now the reason the mask is there is you can think of it like this. So you have the text once again, I love the dogs. What would happen if the word I has access to the attention values of dogs? That's like looking into the future, and that's a no-no. Because when that happens, it'll really mess up the learning process of the AI. And so we can sort of apply a mask to it to prevent it from seeing in the future. That's how that works. Anyways, after you're done calculating the attention values, what's gonna happen is that there's gonna be a residual connection to the model. So the reason they're added is because this model is absolutely massive. And so the more bigger they are, the more harder it is to adjust the weights. And so what they do is sort of add a skip connection. So they'll add the input back to the output to help with the learning process. And then the normalization over here, the purpose of that is in case for any values that are too big or any values that are too small, and sort of normalize it within a specific range. And that also helps out with the training process. Alright, so after the data is added and normalized, what happens is that we'll go through another multi-headed attention without the mask this time, because you've already done it. And then it'll go through the same process of adding and normalizing, and then it'll actually go through a feed-forward neural network, which is simply just your normal neural network. And then the purpose of it is to sort of give time for the model to think about what to actually do with these attention values. And then once again, we're gonna add a skip connection and normalize it. And so we're gonna repeat this whole process an n amount of times, usually 4 to 6. As you can see, that's how big the model is. And finally, we add one last layer of thinking for the model. And we're gonna softmax the final output to actually get a distribution of the word probabilities. And yeah, that's sort of a high-level overview of how the transformer works. And I'll see you in the next video.